Well, I promise this one is shorter than the one on inclines that you watched yesterday. So today we're going to talk about the independence of horizontal and vertical motion with objects in free fall. So it's always understood that gravity is going to cause things to accelerate, but it's only going to make them accelerate in the vertical direction. So if I release an object, after 1 second, it will be traveling at 10 meters per second. After 2 seconds, it'll be going 20. After 3 seconds, it'll be going 30. And it will travel an increasingly greater distance each time because it's going faster constantly. So the acceleration g is in the vertical direction only. If I thought I clicked. Yes, okay. So horizontal motion, however, is not subject to gravitational acceleration. Gravitational acceleration is directed in the earthward direction, which is at a right angle to the horizontal, so it has no bearing on that. So if I throw an object off a cliff at 10 meters per second, yes, it's going to be pulled downwards by gravity. However, the horizontal component of its motion is going to be unchanged. If it leaves my hand at 10 meters per second, it will continue traveling horizontally at 10 meters per second at time t equals 0, t equals 1, t equals 2, t equals 3. It never varies because there's no acceleration in that direction as long as friction is negligible, which in most AP physics problems it is going to be. So the thing is, the object is undergoing two motions simultaneously. At least that's one way of thinking of it. It's both accelerating vertically at a faster and faster speed as it travels horizontally at a constant speed. But the most important thing of all to keep in mind when you're trying to solve problems involving what we call projectile motion, that means objects that are moving in two dimensions as they encounter in a state of free fall, is that the time of free fall is determined entirely by the vertical components of motion. How high it is, what its vertical velocity is, what the acceleration of gravity is. Those are the only things that are going to determine how long the object is in the air. Any horizontal component of its motion has no bearing on the amount of time it's in the air. It has a bearing on how far away it's going to land, but not on how long it's going to be in the air. So just please keep in mind that the horizontal component of motion does not keep you in the air any longer. You drop a bullet, it hits the ground, let's just say, in half a second. You shoot that bullet horizontally at 600 meters per second. It's still going to hit the ground half a second later, just like it did if you just dropped it. The difference is it traveled a long way horizontally. So horizontal motion, no matter how extreme it is, does not keep you in the air any longer unless you're in orbit. We'll get to that later. Okay, so let's try this one here. Classic one. A ball is thrown horizontally off a 30-meter high cliff at 40 meters per second initial velocity. How far away from the base of the cliff does it land? That's a really straightforward question in physics, it turns out. But the strategy here is twofold. Okay, so first of all, I'm just going to draw. That's always a good idea, and I'm going to label what I know. I know that the height, I'll just use h, is 30 meters. I know the initial velocity of the ball going off the cliff is 40 meters per second, and I know I'm trying to find the horizontal distance that this ball travels. Right? How far away is a horizontal question here, okay? So let's see what we're going to do then is, in order to solve for this value here, that's a horizontal distance, it does not accelerate horizontally. This is the one equation that I can use, the only equation I use when the object is not accelerating. I'm constrained to using only this equation to solve horizontal motion problems. Now, I happen to know what the horizontal velocity is. It's right here. It's 40 meters per second. I want to know what the horizontal displacement is going to be. In order to answer that, I've got to know how long it's in the air. Then the horizontal motion has nothing to do with that. It's vertical values. So what vertical value do I know? Well, what I know is the height. That's a vertical value. I'm going to use the height to figure out what the value is for time. All right. So I can rewrite this equation. Let's say delta x equals velocity, horizontal velocity times time. But now I've got to figure out what time is. So I'm going to say, well, here's what I know. I know that height is basically, I can use like delta x equals 1/2 at squared. So I can say height equals 1/2 gt squared. And I simply want to solve that for t. So t is equal to square root of 2h over g. If I substitute in for h and g, so this is going to be 30. So this is going to be 60 divided by 10. So it's the square root of 6. And when I solve that, I'm going to get, I'm just going to do this when I say the horizontal velocity times the square root of 2h over g, and I solve that, and I get 98 meters. The ball lands 98 meters away. Now, if h was greater, the time would be longer, right? And it would go further, right? If I threw it faster, the v would be greater, so it would go further. Let's try this one. A ball is thrown horizontally at velocity v off a cliff of height h, and it lands distance x away from the base of the cliff. Where would the ball land if it was thrown at velocity 2v? All right, well, let's take that same equation we just established, okay? We just established this equation here, that this position here is going to equal v horizontal times t, and t we found is equal to the square root of 2h over g. So now, once I've established this relationship here, I notice that the x in this case here is proportional to v. X equals v. They're both in the numerator. It's straightforward. So if I was to double the v, I would double the x. And if I tripled it, I would triple. But what if we were asked this question? A ball is thrown horizontally off a cliff of velocity v from height h. It lands distance x away. Where would it land if it was thrown from height 2h? Again, I'm just going to go back to that equation I established by using the horizontal velocity equation and then using the height to figure out what the time is. So that's this equation here. And now if I look at this here, it turns out that x, the horizontal distance x, is proportional to, now remember, this and this and this didn't change, so I'm just going to make them one. So really this is just the square root of h. So x is proportional to the square root of h. So if I double h, x is going to go up by square root of 2. Right? Because if I put a 2 here, I get 2 square root 2. That's the new value of x. It's x times square root 2. Hey, that's it. Oh, no, it's not. We're going to do one more. Okay. A ball is thrown horizontally at velocity v. Same thing. But where would it land if it was on a planet that had double the gravitational acceleration? So a planet where gravity is twice as strong. Well, intuitively, it should not go as far because if it's pulled harder by gravity, it will not be in the air as long. It will accelerate faster to the ground. Let's see what we get. We're going to use that same equation. In this case, x is proportional to the square root of 1 over g, or 1 over square root g. Again, I just said everything else that didn't change equal to 1, and I get x is proportional to 1 over root g. So if I double this, the new x would basically be 1 over root 2. So it'd be, x divided by root 2. So it'd be 1.4 times less distance traveled. Okay, that's it, guys. Thanks for watching. Let's keep doing. We're getting good at this, guys.